Hello and welcome. Today we're going to crack the code on one of the most fundamental and, let's be honest, often frustrating data structures out there, the linked list. If you've ever felt just stuck on this topic, you are in exactly the right place. We're going to demystify it one pointer at a time. Let's get into it.
In this quote, it absolutely nails it. The struggle with linked lists isn't really about some super complex syntax or logic. It's a visualization problem. It's about not having that aha moment of seeing how these things actually connect behind the scenes. And that's exactly what we're going to fix today.
So what's the core problem, really? Well, unlike a simple array, where all your stuff is stored side by side in a neat, continuous block of memory, linked lists are different. Their elements can be scattered all over the place. So the real challenge and the key to understanding them is figuring out how these scattered pieces of data manage to stay connected in a perfect sequence.
To solve this puzzle, we have to start with the single most important piece. The fundamental unit of any linked list is something called a node. And I'm serious here. If you understand what a node is, you are 90% of the way to understanding the entire structure. It's that important.
So what is a node? It's just a container, but it's a special kind of container that holds two very distinct things. First, it holds the actual piece of data you want to store, a number, some text, whatever. And second, and this is the crucial part, it holds a signpost, a reference, basically an address that points to the next node in the chain.
Let's break that down. You see the two parts right here. The data is the easy bit. That's your information. The real magic is in that next pointer. Think of it like a breadcrumb trail or a treasure map clue. Each node doesn't know about the whole list. It only knows its own data and exactly where to find the very next node in the sequence. It's a chain of knowledge.
Okay, and this brings us to the real heart of it all. We're going to stop talking in abstracts and actually visualize how these nodes connect to form a chain in memory. This is where it's all going to click.
So imagine we create our very first node. As you can see, it's holding our data, the number 10. The second part, that's its next pointer. And for now, it's pointing to, well, nothing. It's the only link in our chain so far. Now watch this. We're adding a second node with its own data, 20. But look closely at that arrow. That arrow means the next pointer of our first node has been updated. It's not pointing to nothing anymore. It now holds the memory address of that second node. It knows where to find the next link in the chain.
And we complete our little list by adding a third node. The second node's pointer now points to this new one. But look at the very end. That final node's pointer is set to null. You can think of null as a big red stop sign. It tells any program, that's it, the list ends here. And that's the entire concept in one picture, a chain of nodes, each one pointing to the next until you hit that final null.
And this is what that idea, that blueprint, looks like in actual code. You know, whether you're in C++ or Python, the core idea is identical. On the left, you've got a C++ struct with a place for data and a pointer, next. On the right, a Python class with properties for data and next. The syntax is different, sure, but the logic, data, plus a link to what's next is exactly the same.
Okay, theory is great, but let's prove it. Let's make this real. We're going to build the exact visual model we just talked about, but this time translating it into actual C++.
All right, first we define our blueprint in C++ with the struct node. You can see our two key ingredients right there, int data and node star next. We also create this special pointer called head and set it to null pointer, which is just C++ for nothing. The head is our anchor. It always points to the very first node in the list. It's how we find the front door.
So, how do we add a node to the front of the list? It's a simple little two-step dance. Step 1, we tell our brand new node's next pointer to point to whatever the current beginning of the list is. Step 2, we update that main head pointer to say, hey, forget the old one, this new node is the beginning now. Simple and super elegant. Now, to add to the end, we can't just jump there. The code has to literally walk the list. It starts at the head and follows each next pointer from node to node, just like we did with our eyes in the visual. Once it finds a node whose next is null, it knows it's at the end. Only then can it attach our new node.
Deleting a node is all about some clever rewiring. The code finds the node just before our target, and then it reroutes that node's next pointer to completely skip over the one we want to delete. We're essentially bypassing it, cutting it out of the chain without ever breaking the sequence. And how do we actually see what's in our list? Well, traversal is just like walking that chain. The code uses a temporary pointer, starts it at the head, and then in a loop, it prints the data, and then it hops to the next node.
It just keeps hopping from node to node until it finally hits that null stop sign at the very end.
Great. Now let's switch gears over to Python, and as you're about to see, even though we're using classes and some different syntax, the fundamental logic we just established in C++ stays exactly the same. The mental model doesn't change one bit.
So in Python, we use classes. The node class holds our data and next, and it's initialized to none, which is just Python's way of saying null. The linked list class acts as a kind of manager for the whole thing, and its only job at the start is to hold on to that all-important head reference.
Look familiar? It should. It's the exact same logic we saw in C++. We make a new node, we point its next reference to the current self.head, then we update self.head to point to our new node. The language changes, but the core concept of rewiring the front of the list doesn't.
And for inserting at the end, surprise, we're mirroring the C++ logic again. It requires a journey. We start a pointer at the head, we loop through following all the next references until we finally land on that very last node. That's the only place we can attach the new one.
The logic for deleting is identical. Find the node before your target. Once you have it, you just update its next reference to jump over the target, patching it right out of the sequence. It's the same pointer bypass trick, just with Python syntax.
And finally, printing the list. We create a temp variable pointing to the head. We loop as long as temp isn't non, and in each step of the loop, we print the data, and then we move forward. Temp equals temp.next. It's that same hopscotch logic we saw in C++.
So, after all that, what's the one thing you absolutely have to remember? It's that the code, the syntax, that's just the detail. The real key, the insight that unlocks everything, is that visual model of nodes being chained together by these pointers. And we'll end on this powerful piece of advice. Everything that seems more complex in linked lists, doubly linked lists, circular lists, crazy algorithms, it all builds on this one simple foundation. Master the visual of the node and the pointer, and you've truly mastered the core concept. And suddenly, what seems complex is just a chain of these simple ideas.